Welcome back to Launchpad. I'm Christian Reddy, your friendly neighborhood astronomer, and it's great to see you here live and in persons, or in digital binary bits, whatever it is we're using. So, I am happy to welcome you tonight, and we're going to be meeting tonight. This is not part of our regular planetarium meeting, by the way, at Towson University. Instead, this is just an informal hello, how you all doing type of thing. Because I got a buddy of mine who's coming on tonight who's going to be talking to us about testing some of the fundamental properties of physics. Some of the things we've always taken for granted or assumed was always true, but maybe never really fully formulated the proper test for it. And really just trying to get to the nitty gritty of our universe. He is, in fact, the author of Losing the Nobel Prize, a story of cosmology, ambition, and the perils of science's highest honor. He is, in fact, the man himself, Dr. Brian Keating. Hello, Brian. Good evening.
Hi, Chris. How are you doing tonight?
I'm doing great, and I'm getting an echo in my ears. So I gotta just make a little adjustment here. Pardon me. Shut
All
off
right.
this stupid op.
I can also plug in my headphones.
Yeah, if you don't mind putting in your headphones, that would be super helpful.
Absolutely.
All
Anything
right.
for
Yep,
you.
everybody, this is live, and we didn't exactly get 100% of all of our stuff sorted out just ahead of time. I do want to say hello and just welcome a few folks here. I want to welcome Jan Pathmedic. Good to see you. Lucky Lucy, hi. How you doing? Serg. We also have Create You saying, I seriously love that book title. It really does, and there's quite a story behind that, Create You. You got to check that out. All right. Let me
Is that
see if
better?
I
Can you
can
still hear
also
me?
say hi to some other folks. I got hi Christian, hello everyone. It's good to see you. And Brian, you've got your earbuds in, but I honestly have no idea why I'm getting this wretched echo. I hear you just fine. Pardon me as I. Okay, Brian, you there?
Yeah, I'm here.
Okay.
Here.
I'm hearing the entire thing play out, and I think I know what the problem is. I know what the problem is. You see, I actually had my own live stream up in another browser, and I wanted to see the comments come in, and I actually had my own browser talking to me, and it was really, really strange. I hope everybody else can hear me, and bear with me as I learn how to live stream goods. All right, let's talk a little bit about what's going on, Brian. So you've written this book about losing the Nobel Prize. I know we spoke about that the last time we had you on.
Yeah.
Okay, good. I'm delighted to hear that sound is good there, and it was purely just on my end, so that's wonderful to know. Thank you. Anyway, Brian, I'd like to ask you a little bit about how you go about investigating some of the fundamental properties of physics itself and testing it. And let me guess, you're going to tell me it has to do with a cosmic microwave background, aren't you?
Well, in part, it's everybody's favorite fossil. And we astronomers, as you know, are nothing if not archaeologists of time,
Yep.
using our time machines, aka our telescopes. I have one here that is my first telescope. This is about 45 years old. No, this isn't my first one. This is, I think, a pirate used it and dropped the lens out of it. But when Galileo first looked up at the heavens, he was using a telescope, not unlike the one I just showed you. Here he is now. My friends at the Unemployed Philosophers Guild sent me these beautiful finger puppets of Galileo. We'll talk about Einstein. We'll talk about, there you go. Are you giving me the finger?
No,
Galileo got in a
no.
little trouble for doing that himself.
Galileo, I wear Galileo on my middle finger for a very specific reason. Anyway, go ahead.
uh, yes, you and other Christians. Just kidding, just kidding. Now, that's a double entendre, as they would say. So, what we try to do is use these telescopes to learn about phenomena that are insufficiently uh, distant to check in our laboratory. So, imagine there's some phenomenon that changes the nature of the properties of light or changes the nature of the properties of gravity. Well, these things might be true, but we might be unable to measure them here on a laboratory and on Earth, such as my
Right.
laboratory here at UC San Diego. So instead, we have been given one of the world's, or if not the universe's, greatest possible laboratory, and that's the universe itself. And so there are distant phenomena that are exotic that could provide ideal laboratories for testing matter under extreme circumstances, for testing the laws of electromagnetism, for testing the principles that underpin all of modern physics. And that is something that is really a key ingredient in Einstein's theory of relativity. And that's something that we'll talk about today, which is a special kind of symmetry known as Lorentz invariance. And I have been obsessed with this for years, decades now, and we're finally getting to the point where we might be able to test it and see if the universe violates this closely held principle.
So let's talk about what is Lorentz invariance. Obviously, the name implies something shall always be the same in different frames of reference. But let's go ahead and just break that down a little bit and talk about what that is and how we might go about testing it.
Yeah. So the most simple way to encapsulate the essence of what Lorentz invariance is to say the universe doesn't care about you. I'm sorry, Christian. I care about you. Your fans care about you.
I care about everybody. Yeah.
The universe couldn't care less about you. Doesn't care where you live, what your color is, what country you are in. Yeah, it doesn't care. And in fact, find very important, such as what day today is. We have to make an appointment to schedule this live stream with your audience. Well, we had to set the time. The universe doesn't care about that. The universe goes on about its business and really doesn't respect anything about us from our perspective, because it is just ours. In other words, if I take observations of the planet Jupiter on a Wednesday, and I come back, a day later, and those general observations, maybe the exact phenomenon won't be the same, but the general properties will not vary from day to day, from hour to hour, from second to second. And so one way that you could test that principle of perhaps the uninterested universe is to look for variations. Perhaps there is some universal time that the universe is aware of, or some universal energy, or some universal length scale, or color, or gravitational effect. And we don't believe those are true. And in fact, that is the basis of Einstein's theory of what's called special relativity, that the universe doesn't care what your reference frame is. You and I have equal share and equal claim to being the center of our own universe, which means there is no center of the universe. If every observer can claim to be the central observer, that means none of them are. And that is the key realization that led us to try to test whether or not this is true. Because if it's true, then everything is well, and all of physics on which we base all of modern laws and everything you teach to your students would be held near and dear and still correct. But if it's wrong, then this guy is wrong. And that would have unique implications for all of our understanding of science, not just physics.
That's extremely relevant. I mean, yeah, as you said, that is as far to the core as you can possibly go. We essentially claim, or we believe, that we live in a universe where we hold no special place, we hold no special privilege of position, or in theory, moment in time, except for the fact that we had to wait for the universe to get old enough to have us around. But we are now thinking about, we're basically saying, look, if this is not correct, then there actually is an absolute frame of reference. Is that what you think that might lead to?
There have been claims that there are absolute frames of reference, and this goes back a long ways. It goes back to even the pre industrial and scientific revolution theories of none other than Galileo himself. And that was first kind of elucidated in what I consider the second best science book ever written. And that is, of course, the dialogue on the two chief world systems. And in this book, which is written, the foreword of which is written by none other than a man by the name of Albert Einstein, he calls it one of the most important books in history too, not just for its scientific content, but for the way that it presents these arguments in a way that people could understand it. It was written in Italian, It was written in a way that the common person could understand it in the form of a dialogue between multiple characters that were loosely based on real human beings. And this is the famous book that got Galileo into a little bit of hot water with the church. We don't have to get into that necessarily. But the main idea of this polemical book was to establish the scientific basis of the Copernican theory, namely that the Earth is not the center of the universe, and that the sun is the object around which the Earth and all the other planets go. And that was revolutionary, no pun intended, because that's the title of course, Copernicus's book and his hypothesis on the revolutions of the heavenly spheres. But what Galileo wanted to do is take that hypothesis, that was just a theory like the theory of evolution, which has no basis. No, I'm just kidding. I believe in the theory of everything. I'm just testing you, Christian. But the theory of of the Copernican theory
it doesn't matter what we believe, actually. Reality wins 100% of the time, right?
Exactly.
But anyway, go ahead. I didn't interrupt you. Go ahead.
Yeah, so Galileo wanted to establish scientifically, using the scientific method, to establish evidence, deductions, inductions, hypothesis correcting, and consensus, the cornerstones of the scientific method. And he's really considered the first scientist of the modern age to employ it. And it's interesting that when he set out to do it, his job was trying to prove that the Earth went around the sun and not the other way around. And by a real kind of series of events that are almost comically hilarious, he both attributed the effects that would be the most proving cause, the most strong evidence for his hypothesis. He made a completely fallacious argument that we now know to be completely wrong. And that was the original title of his book. This was the title that he eventually was forced to publish by the church, the dialogue concerning the two chief world systems. But his original title, get this, I consider this for losing the Nobel Prize also, but his original title, Christian, do you know what it was?
No, I don't, actually.
It was very catchy. It was On the Flux and Reflux of Tides in the Earth's Rivers, Lakes, and Ferns. Ferns. I don't know if they have ferns by you over there in the East Coast.
Well, we have a few here and there, but I mean, I think
ferns in Maryland.
Clearly, yeah, we have Maryland ferns, but clearly, the church did not want Galileo on the New York Times bestseller list. That's why they made him go with on Dialogo. Yeah.
Yeah.
Did the church not realize that this book was kind of trolling them, and that they were making it, by changing the title, they were making it that much more accessible and likely to be read by people?
Well, it's interesting because Galileo was formally charged with violating an injunction back in 1616, and that was to not teach the Copernican system. It was fine to research it. It was fine to observe it. And this book, I should say, was published in 1632, so 16 years later. And it took him the better part of a decade to actually write it. It's actually 587 pages long with footnotes and introductions. So it's quite a lengthy book. I have read it cover to cover. And there's some dry parts, but there's some parts that are just spectacular. And I think what threatened the church so much is that he, unlike the first book that really elucidated the image that we associate with Galileo, namely the moons of Jupiter, the craters on the moon of Earth, the phases of Venus, all those observations were made in a book called Sidereus Nuncius. And I know that you know Latin. I'm speaking as a fluent native, but I don't. But anyway, that book is written in Latin. That was not written in English. In English. It wasn't written in Italian. So he was permitted to espouse those ideas because that wasn't considered teaching. It would be like your university says, Christian, you could teach as long as you do so only in Python 3. And then you're like, well, Python 3, it's not really as good as, Fortran, whatever. And so you misconstrue their direct order. Now that's permissible with some university administrators think that they have more power than the Pope. I know I suffer from that sometimes, but nevertheless, the Pope was the most powerful person in the world at that time, a governmental, military force, etc. And they had the power to basically accuse him of teaching it, which was a condemnation, which carried with it a penalty of essentially suspicion of heresy, which could be a capital offense, either leading to execution or to lifelong imprisonment. And of course, he was imprisoned, but it was a pretty sumptuous surroundings where he was imprisoned. I actually did a conference on the basis of relativity, which we'll talk about just in a second. But Galileo was the first person to really investigate what we now call relativity. And I hosted this conference with friends outside of Florence at Galileo's prison, quote unquote, which is in the mountains or the hills behind Florence, what's known as Arcetri. And it's a beautiful, sumptuous villa with grapevines and orchards and so forth. And I always joke, Bernie Madoff would kill literally to do his home imprisonment there. So what Galileo did that was so brilliant in this book is multifaceted, because it reveals science as done by human beings, not only by, as I call them, walking Wikipedias. He was human. He had human foibles. He had failings. He had biases. He had prejudices, just like you do, just like I do. And science is done by human beings. So why would we expect science to be free from such biases?
Sure.
I think it's even more relevant today than ever.
And that's why we have peer review, among other things, plus not to mention just general scrutiny from the community as well as the public in some cases. So with that, if we fast forward by 400 some odd years...
Yeah, well, let's go first.
Where does this take us
slides.
to?
Yeah, let's look at the slides that I show.
Okay.
Because this is the main argument that still holds water, no pun intended, today, which is, this is taken from Physics Central, which is from the APS. And it shows what's known as Galilean relativity, in which Galileo said that if you were in a boat underneath the surface of the boat, and you blocked out all the light, etc., and the boat was moving in uniform motion and there were no waves to speak of, then this vector up top, the black arrow, is showing the direction of motion. Then anything that you did, any observation, any experiment that you did would have the same outcomes as it would on stable, dry land. In other words, you could do an experiment where you drop a ball at T1 and it lands at T2, as shown here. And the position of other objects at rest to you would measure different behavior of that ball from their reference frame. But you could add together the velocity. If you threw the ball, you could throw the ball inside. There's Galileo. He could throw the ball also. And the velocity of the ship would be added to the velocity of the throwing of the ball. And so he said you basically couldn't do an experiment on a boat at constant velocity, which would reveal the motion of the boat, which we now know to be true. There are subtle effects to, if you think about the Coriolis effect. So Eugene, very good. As I'm saying it, Eugene Seidel gets an extra bonus point. The Coriolis effect, their effects. You've got a good audience. I know I have an awesome audience, and they're watching too. But that was great.
I am so proud of them.
Yes. So that's a subtle effect that would reveal what's called a non-inertial nature of the motion of the Earth in rotation. But let's ignore that. And Galileo ignored that. And so their thing stood for 300 years at least, until Galileo came about and said, well, that may be true at low velocities, but if you increase the boat's speed near the velocity of light, other things start to take over. And in such a situation, you could not claim that physics would still not depend on your relative motion, and no one observer could claim to be the most important observer in the universe. And that was the underpinnings of the Lorentz transformation.
Right.
But
we expect everything to be the same in all frames of reference. Okay. Very good.
After Newton's...
By the way, just if the story sounds awfully familiar to me, and I'm sure to anybody else who's learned about relativity and things like that, Einstein was using a train, Galileo's on a boat, same thing.
Yeah. Yeah, isn't that funny? And we've all had that experience, right? Where I literally have had that on a train, on a boat, on a plane as it taxis away from the gate. You feel like the other objects are moving and you feel like you are stationary.
Yep.
And so, but think back then, we have the benefit of standing on the shoulders of these giants. They didn't know it. And so, but remember what Galileo wanted to really prove is the diagram. Ignore the luminiferous ether for 1 second, but he wanted to prove that the Earth is moving around the sun. Mm-hmm. In other words, the Earth, if it was moving in this fashion, and if the orbital radius were large enough, then effectively it's almost like that boat and you couldn't discern it as people claimed that you would feel the velocity of the Earth if it were really in motion. And so that was the notion that held from Aristotle up until Galileo. And so because of that, Galileo kind of rebelled against it and started to say, well, no, don't demand that it's possible for us to determine that we're in motion from simply the motion or things that could depend on your reference frame. And so what he instead tried to do is argue that the motion of the Earth combined with its revolution on its axis and its rotation about the sun would cause a sort of sloshing effect, like in this cup of whiskey that I'm holding up. That's good whiskey. I actually have behind me some Simon's Observatory whiskey. I don't know if you can see that. Anyway, that's not whiskey.
Something for the after show. Yeah.
It's not yet. It's only 9 a.m. where I'm at. I only wait till 10. No, I'm just kidding. So going back to the slides, so their thing stood for a very long time. And in fact, the true explanation for the Earth's tides has nothing at all to do with the motion of the Earth around the sun or around its axis. Instead, it's caused by the tidal gravitational pull of the moon. And so it was interesting that Galileo, some believe that he knew that to be the case, but the argument, kind of the visceral appeal of that argument that I just did with this cup of water, it was so persuasive, not only to him, but he knew he could convince others of his conjecture, which is ultimately true, right, Christian? It's true that the sun is not going around the Earth. It's the other way around.
I'm pretty sure, yeah.
Is it okay for us to use like incorrect logic to like establish something that you know to be true and it must be true? No, I don't think so. Any more than it's good to lie to people, your kids or something. But I'm a parent and I don't know how to do stuff without bribing and lying and all sorts of chicanery. But anyway, that's besides the point. So getting back to these slides, so if their thing stood until Newton, Isaac Newton didn't really add much to this theory of relativity. He did add to the theory of gravity, which firmly established that the moon caused the Earth's tides. But getting back to relativity, it really wasn't until James Clerk Maxwell in the 1800s came up with the theory of electrodynamics. So how electrical and magnetic waves propagate through space was governed by a term that had, in effect, the speed of light as the propagation speed. And this brought up huge kinds of intellectual dissonances. People just could not accept the fact that, A, you could have things traveling through a vacuum. They would say, well, there must be some medium, just like there's water waves in the Earth's tides and in the for water waves or air waves, carry sound waves are carried in a medium. They said, so too must Maxwell's waves of light be carried on some substance. Otherwise, you'd have this spooky action at a distance, so to speak, although that was reserved by Einstein for much, much later. And so what I found so interesting is that because of what Galileo proposed, then when Maxwell came along, he was really kind of stumped for a while, and it really fell to Poincaré and then much later Einstein to come up with an idea that no, it is possible for people to tell to do experiments that are occurring near the speed of light that violate Galilean relativity. In other words, that you can simply add the velocity of the ball to the velocity of the ship. Einstein showed that with the postulate of what's called Lorentz invariance, which is that there's no preferred reference frame in the universe, and another postulate, which is that the speed of light is the maximum possible speed of any transmittable information, physical body or object or signal. Those two postulates effectively allowed him to propose what became known as the theory of relativity. And around that time, there were experiments being done actually at my alma mater, Case Western Reserve University in Cleveland, Ohio. There was an experiment done by Michelson and Morley to test whether or not there was a type of water-like medium through which waves of light here from the sun, for example, or from anywhere, that would support the oscillation of waves of electricity and magnetism. And so they devised a test. They said at different times of the year, if there is this luminiferous ether, and it is a region of space in which the Earth is, it supports all oscillations, then the Earth will be traveling at different times with respect to this luminiferous ether. And you could add the velocity of the Earth in the to the velocity of the ether in the spring or summer, and you could subtract that in the fall, and you should get different values for the speed, or for this particular phenomenon would vary with time of day. As I said, you can't. That is a forbidden fact in notions of what's called Lorentz invariance. So they devised a test, which I show on the next slide, which was actually done at, as I said, at Case Western, which used an interferometer. I'm just showing you because it looks kind of cute. I'm not going to get into too much detail. But they ended up getting a null result, meaning that they could not detect the Earth was moving with respect to this ether, this luminiferous ether. So either there was some phenomenon taking place that conspired that throughout the year, the measurement of the speed of light would be constant. Either that was occurring, or there was no luminiferous ether. So what I think is so interesting is that in actuality, one interpretation that's Lord Martin Rees made on my show Into the Impossible on my podcast about a month ago, is he said, if you think about that in the context of Galileo's adversaries, they would have said, thanks for proving us right, Galileo, because it really could be used to show that the Earth is stationary. So isn't that ironic that, this cornerstone in the theory of relativity of Einstein could have been used to refute the claim that the Earth is in motion? That's just kind of a cute and ironic aside. But the ultimate discovery by Einstein was that Galileo's relativity only held true at very low speeds. And in fact, you have to augment that when you want to test things at higher velocities near the speed of light. And so what we're trying to do now is not only use phenomena that take place at very great energy levels, perhaps the origin of the universe that I talked about the first time I was on the show, but also look for violations of this principle called the principle of Lorentz invariance. Namely, the universe does not care if you do a measurement in the spring or the summer. It doesn't know anything about our local reference frame because it is ultimately insignificant, unimportant, and other things that my older brother used to accuse me of.
Wow, that's a great introduction to the. So now we are trying to Actually, before I get any further, I do want to just acknowledge just a couple of comments before I get to what I was going to say, and that is, there's a few questions that have come up. Ted, what we're going to do, we're going to come up to some questions in a little bit, and I'll just be scrolling back through these as best as I can. But what I'd like to just ask is that, we're looking toward the microwave background, and we're trying to see, because it's, on the one hand, to a lay person, it might seem like, oh, well, the microwave background's got to be the ultimate reference frame. After all, it surrounds everything that we see. It's permanent, it's everywhere, it's uniform to within one part of 100,000. There you go, right? There's our ultimate reference frame, right?
Well, people do say that quite often, and I always say there's no such thing as a stupid question. There's just stupid questioners. No, I'm just kidding, Christian. That's totally a legitimate.
I asked that question on purpose.
So no, it turns out that what we call the cosmic microwave background is better thought of as an event rather than an object. So in the sense that the microwaves that we detect using telescopes like currently the Simons Array and upcoming and BICEP and then upcoming Simons Observatory, we are able to measure the properties of the universe when it was about 380,000 years old, and the light and the material composition, and whether or not there was exotic form of radiation called gravitational waves, not unlike what LIGO detected from the collision of two black holes. That was the subject of my book, and that's the subject of our previous conversation. Now the question is that reference frame absolute? In other words, can you tell somebody to meet you at a certain day, at a certain time, at a certain altitude, north, latitude and longitude? Can you use the cosmic microwave background to do that? The answer is no, because that observation of how we perceive it is unique in the sense to its actual properties. In other words, it's specific temperature in that direction over here versus that direction over there. depends on where we are on the Earth going around the sun. So in other words, we see local effects, just like our galaxy is very similar to about 100 billion other galaxies, but it's not identical to any of them. So in other words, the statistical properties of these microwaves, as you say, are independent. They have a certain characteristic, but we can no more say that we are able to measure our position and time with respect to the microwave background than to do so with respect to a given explosion. Say another event was the dropping of the atomic bomb on Hiroshima. So that was an event that took place at some space, at some time, and yet we cannot measure things specifically related to that in a way that holds true on Proxima Centauri b. In other words, those two times and those two coordinate systems do not overlap in a way that we can stitch together to make a universal coordinate system. And the same is true not only within our galaxy, but within the entire observable universe.
Perfectly legit. Yep. Okay, great. So then, how then can we use the cosmic microwave background, even if it is not the ultimate reference frame? How can we probe that to test these ideas?
So what we want to do is, instead of looking for, and it's not only the cosmic microwave background. I'll actually talk more about individual sources as well. There was a claim recently that it would be possible to measure the violation of something called parity symmetry. And parity symmetry is the other very closely held belief that physics should look the same in a mirror. In other words, if I show you a pendulum going back and forth, and I say, actually, Christian, you were looking at that through a camera, so it's like a mirror image, you can't tell the difference. The physics is identical. If you go underneath the plane of the solar system and look up, you would see planets going around counterclockwise or what have you. I believe counterclockwise from below the plane of the galactic of the solar system, the ecliptic plane. Now, if you go above it, you could say, well, now they're going in opposite direction, so all you have to do is reverse the direction of time. And then you get the same laws of physics. Physics does not have any dependence on absolute time. And it doesn't have dependence on absolute left and right symmetry for most laws of nature. But it turns out there is a principle known as the violation of parity symmetry and charge conjugation. So these are there are three different types of symmetries. If you change an electron to a positron, it will behave the same as an electron with an electric field reversed. Okay, so that's charge symmetry. Parity symmetry means that physics will look the same in a mirror, and that you won't be able to distinguish the physical laws of a pendulum oscillating or a spring vibrating or whatever if you're looking at it in a mirror. And time invariance, as I just said, if you change the direction of time, you should not actually be able to tell that, actually I'm running the movie backwards when I show you this pendulum. You can't tell what's happening, what's forward and what's backward. So these are all discrete, what are called discrete symmetries. Turns out in the 1950s, scientists discovered that there's a law of nature, and it's called the weak nuclear force. And the weak nuclear force does violate two of these symmetries. In other words, you can tell that you're looking at physics of the weak force, which is nuclear decay, governs nuclear. You can tell that the cosmos violates that in a very, very subtle fashion by doing an experiment that was done in 1957. So this isn't like requiring like the Large Hadron Collider or something. This is very, very, and this is called violation of charge and parity. This was discovered in the 1950s. Now, there's something you might be familiar with, which is something called a theory of everything. Have you ever heard that?
A few times, yes.
Yeah. So a theory of everything
I'm still working on it.
Yeah, exactly. That's right. I usually ask my guests when they come on my show, you owe me an appearance. This is now the second time I've invited myself on your show, so I want you to invite yourself on my show.
Okay, I'll invite myself on the show, but I don't know if I can hold a candle to some of your other guests. This guy gets the best guests right here, and now he wants to have me on.
I definitely want to have you on. You're one of my role models and inspirations. But let's not get into a mutual admiration.
But back to that. Back to mutual. Back to theory of everything.
So if you show the screen now that I'm sharing,
sure,
I will point out a couple of facets here. There is a kind of set of blocks shown here that are meant to kind of encapsulate what we know about the laws of physics. So there are laws of gravity at the top. There's laws of electromagnetism, of chemistry. There's something called the standard model. That's the laws of particles, forces, and fields. That's shown up here in the upper right corner. The quarks, the gluons, the W bosons, the neutrinos. All those forces, we believe, were once unified together into what is typically called a theory of everything. And that theory of everything could be a true statement about how these forces become one at very, very high energy scales, which translates to very, very early times. We don't know if that's true. We have reason to suspect that that's true. And I have several videos from this past summer with PBS Spacetime Studios, where we asked leading contenders for theories of everything to kind of go through their arguments and attack their competitors. And it was really fun. So check that out on my channel.
It was a wonderful series. That was a wonderful series.
So the question of whether or not it's possible to look for deviations. So now if we go to this diagram and I slightly break this assumption that the universe doesn't care about you, that doesn't care what day it is, doesn't care where you live, doesn't care what you look like, that will have downstream effects. It will have effects that ripple through potentially to allow test for the existence of this tiny violation of Lorentz symmetry far, far downstream, potentially in the realms that I traffic in, namely cosmology and astrophysics. It may also have implications for gravity in that we would see it manifest itself in a very interesting way via gravitational waves. Like LIGO would make different detection, if you will, on a Monday versus a Tuesday in a way that I'll explain in just a bit. So this is the underpinning. If we can find a downstream effect in astrophysics and in the laboratory, some deviation that elucidates the violation of Lorentz symmetry, it would perhaps have, even greater ramifications than whether or not the universe began with an inflationary Big Bang, as you and I talked about last time. So this would be new physics. It would mean that the laws of the standard model of particle physics, of gravity, of GR would have to be modified at a very, very deep fundamental level. So we should look for it.
That would be something else, because it's not the first time we've seen competitive theories to general relativity. One of the ones, and I can't remember who the author of it was, basically gave a colloquium when I was at the university, saying, here's my theory, and he talks about all these wonderful parameters that he can tweak just to get to. And I'm thinking, so wait a second, your theory requires you to tweak parameters to arrive at a specific. That's not a theory. So how can something like this be tested? Straight, you might say. Like, what would be a? This is an interesting prospect, and I know Brian.
Yeah.
Sorry, I've got.
Yeah. Can you hear me still? It went a little quiet.
I'm sorry. Can you hear me? Yeah. Okay.
Now
I
hear you. Yeah.
Sorry, I'm sorry. I was muted.
That's okay. Yes. So.
Well. Yeah. Well, you too, Elisa, because you're watching us.
You can hear me okay then, Chris?
We got you good. Yep.
Okay, great. So back to what we can actually say and why it's so important. So we think that the universe obeys these fundamental, dearly held principles. Yeah. That doesn't stop people from conjecturing ways that we could violate this principle and, in some sense, perhaps elucidate how the theory of gravity gets unified with the three higher energy forces: electromagnetism, the weak force, and the strong nuclear force. Mm-hmm. And I should say, as an aside, we do know that electricity and magnetism are unified. Electromagnetism is the name we gave to that. That's what Maxwell did. In the 1960s, a past guest on my show, Sheldon Glashow, and Steven Weinberg and Abdus Salam showed how the weak nuclear force is actually another manifestation of electromagnetism at high energies. So that was called SU2 unification. And now,
that was the electro weak theory that we now have.
So I just told you that in the 1950s, people showed that the weak force violates parity. Then you should expect that perhaps maybe at high enough energies, and you can read that as early times, that the electromagnetic force would manifest parity violation. And how would you detect that? Well, you might see the following phenomenon. You might see in the early universe an explosion that is polarized, produces polarized light. ignore how that occurs. It's known to happen in the microwave background. It's known to happen with supernovae explosions as well. And in fact, it could happen with gravitational waves emitted from the coalescence of black holes, for example. Now, imagine these waves of light are produced, and one polarization, in other words, one orthogonal component of the electromagnetic field, the light in that polarization arrives in your camera 1 second before the light arrives in the horizontal polarization. That would be a manifestation of parity violation, which itself would not necessarily violate Lorentz invariance, but you can trivially modify the laws of Maxwell to do both parity and Lorentz violation. And that's been a claim that was discovered not just once in the history of cosmology, not just once in the history of my career in cosmology, but so far about 3 or 4 times people have claimed, including at the end of last year, that the universe disobeys parity symmetry in electromagnetism based on observations of either radio galaxies or the CMB. And perhaps it violates parity symmetry or Lorentz invariant symmetry as well. So we start to look for that. And it turns out the deeper I go into it, the more kind of unusual and the more interesting the implications of the measurements that I'm doing turn out to be. In other words, we may be able to get at the heart of these questions using both the cosmic microwave background and looking at these distant objects that are called radio galaxies or quasars, and they may illuminate what the properties or the symmetry properties of nature really are and to what extent they are violated.
That's remarkable. That is, and I'd like to ask about, because I know you got like someplace you want to go with this, and so I want to let you get there. But I also want to kind of talk a little about how you go about actually doing that. What these observations would look like, what these experiments would look like. First, though, I do see something in the comments, and I want to give a shout out to James Overdoin, good friend of mine from Towson University. Constraints on Lorentz variation are very strong. If we strengthen them further and still find nothing, theorists will simply move the goalposts. Is there a level beyond which we can stop looking? Great question. What do you think, Brian?
Well, I agree. I'm an observer, not a theorist. However, there are. I actually had a conversation today on my channel. I recorded an interview with Carlo Rovelli. So if you go over to this PowerPoint or to the keynote slides, you'll see a bunch of book covers, and some of them are involving this particular type of theory of quantum gravity, known as loop quantum gravity. And loop quantum gravity has been around for a really long time. It's a true contender, along with string theory, for a possible way to unify gravity with quantum mechanics. And that's the holy grail that I think is interesting to probe. Now, the limits are strong. They're strong in the laboratory, but they claim, and this is the claim of Carlo Rovelli that I had on my show, which will come out hopefully in the next few weeks on the Into the Impossible podcast, that actually the Lorentz invariance violation that was predicted to occur and claimed not to exist is actually not that strong, according to Carlo. In other words, the tests that have been done do not really rule out this effect in a meaningful way. And the effect that was claimed to be dispositive, to kind of refute the loop quantum gravity's claim, he involved what's called a gamma ray burst. So a very energetic explosion of an object at very high redshift at very early times in the universe's history. And that produced photons of many different colors, including very long wavelength photons in the red end of the gamma ray spectrum, and very short wavelength in the blue end of the spectrum. And these photons, according to the claims that were made by those that were probing this effect using the Fermi satellite, was that the red photons would arrive later than the blue photons. So in other words, you could test the energy dependence, which is one of the terms of the so-called violation of Lorentz invariance, would involve violating the independence of energy. In other words, the speed of light should not depend on what color light you're using. That is a form. So Carlo today and elsewhere has claimed that no, it's actually not true that the universe has been shown not to have this effect. And in fact, he thinks it's alive and well in quantum gravity of the loop variety.
And this is after accounting for all the effects of extinction, dispersion. He still feels that there's.
Yes.
Oh wow, that's fascinating. Okay, this is the
Yeah.
first I've heard of this, so this is news to. I'm hearing it
Yeah.
here.
It was a great conversation.
That's
Yeah, it should be
fantastic.
out fairly soon. And
Good.
of course, he has a deep interest in this because, one of the notions that this can impact on is sort of a notion of time and how time is measured and to what extent time is absolute, relative, the different types of time that people talk about, how we experience time. And so it is true to your listener is very astute there, but there's actually a rich literature, and every 3 years there's a conference held at Indiana University, and it's by one of the leaders in this field, and they look at the literally 800 different ways or more that you could violate the standard model of electromagnetism by adding a parity and Lorentz violating term. And there's 800 different ways or more to do so. And very few of them have been ruled out definitively.
Okay. But then again, they've also not yet been ruled in as almost like the simple contrapositive of, but you know what I mean? Like, have there been any, so like what experiments are being done to, and we can't talk about every single one of them, but I would like to talk about how the experiment would work. Like, what would you actually be looking for? Would this be another bicep 2 type of experiment? Would this be something else? Tell me what you have in mind.
There are ways to look for this effect in the microwave background. I'll skip over the math because I think it's a little bit pedantic, but it's just cute in one sense because it involves the very man who's funding the Simons Observatory, namely this guy, Jim Simons. He came up with a concept in mathematics known as a chern-simons invariant, which is really an object that belongs properly in geometry and differential geometry and manifolds and topology, but for various reasons it became possible to have application in not only string theory, which Ed Witten has used this chern-simons term. And I'm also trying to get Ed Witten on the show, but so far he's my impossible get into the impossible, but we'll see. I'll keep working on him. I don't give up that easily, Ed, if you're out there. I know you're listening. But it also has implications for cosmology. So string theory and cosmology together, they offer ways for us to think about and possibly constrain the existence or lack thereof of these exotic effects. So I want to point out what we're doing here at UC San Diego with colleagues at MIT and elsewhere to really uncover, decode whether or not you could measure such an effect using optical polarimetry. Now, why is this interesting? Because an optical experiment can cost 1% of the cost of a microwave experiment, or 1/1000% of a space telescope like the Fermi telescope. In fact, some of your listeners might be able to help in such a campaign. I do want to take the advertisement opportunity to ask you to sign up for my newsletter, briankeating.com. You'll get a lot of cool information. You'll get links to interviews with Jim Simons, with Shelley Glashow, with Frank Wilczek. And I also have a giveaway to win a book by Frank Wilczek, who is just on my show, who has a term of his own which violates CP variance called an axion. We're not going to get into that. But I do want to mention that for you amateur astronomers out there, we are working with a very talented amateur astronomer. He's also an alumni of Case Western University, it turns out, named Gary Cole. Anyway, he lives in Western Nevada, outside of Reno, Nevada, and he and I have become friends. And we've been using his very sensitive but amateur-built polarimeter that's shown there to measure these effects for objects known as blazars, which are a form of active galactic nucleus. And by measuring them over the entire sky, we can look for effects that are both very distant, and so sample a large fraction of the cosmic volume, which is shown by this funnel kind of shaped thing over here. This is the WMAP picture of the universe's evolution. But we can look for these Lorentz and CP violating effects that would be the hallmark of new physics. So I'll just go over this very briefly. This is the team. Very tragically, unfortunately, my good friend and colleague Andy Friedman, who is the leader of this project, passed away from a series of illnesses of this past summer in 2020. So we dedicate everything we're doing in this project to his memory and to
Oh,
his
I'm so
legacy.
sorry to hear about that.
Yeah, he was just turned 41, and he was a
Yeah.
real giant, and just a hilarious, humorous, good-natured, individual who did so much, not only for me, but he also mentored this young man over here, Isaac Browdy, who is now a freshman at UC Berkeley up north. And Isaac won the San Diego Science Fair under the tutelage of Andy Friedman and myself, and also came in fourth in the whole state of California
Man.
based on the project that we did together. So he was a mentor, he was a friend, he was a giant of a scientist. So in his memory, we are continuing this term. And really what it comes down to schematically is we can look for violation of the standard model of physics using distant objects, in this case, using the objects known as blazars, and mapping their positions on the sky, looking at their polarization properties, seeing how they vary in space and in time, and looking for preferred reference frames. And in so doing, we can limit both Lorentz invariance violating terms here, or CPT, charge, parity, and time violating symmetry terms here. And I won't go into the details of how many different terms, but I already mentioned there could be literally, 10 to the third different ways that you could violate and so far escape current bounds. But what's shown here is why it's so interesting, because you might see effects such as those predicted by loop quantum gravity, namely the discretization of space-time itself. So Carlo Rovelli, Lee Smolin, Abe Ashtekar, and others conjecture that we've been going about quantum gravity all wrong. We've been trying to make gravity quantized, but really the thing that is quantized is space-time itself. And in so doing, you can make laws that are self-consistent that seem to agree with some data, but have challenges with others. But compared to string theory, which has had 10 to the third more people working on it and 10 to the third more dollars devoted to it, it's very promising. And I really encouraged by my conversation with Carlo and Lee Smolin and others that it's something to look at, because if you could find this Planck scale features, the only hope you could find them of finding them perhaps is when the universe was about the Planck size. Planck size, I should remind you, is about 10 to the minus 35 meters. So we're looking for, quite small distances. And the speed of light, the Planck time is that distance, divided by the speed of light. And so it's incredibly small. It's 10 to the minus 43rd of a second. So these are really just infinitesimal amounts. But what's so good about that, Christian, is that it eliminates and alleviates the need for these so-called singularities that develop in quantum gravity typically.
Because you can never get to zero. If we're describing space-time as, okay, it's quantized, there's a minimum length to the universe, there's a minimum amount of time.
You never divide by zero.
You never divide by zero. I've always wondered about,
unlike how I do my taxes,
Yeah. I've always wondered about that, which is not to say that I'm like genius, but I've always thought to myself, okay, can't we just treat the space, the Planck lengths and the Planck times as discrete units in the universe? And it's exciting to see that there's a line of work that's heading in that direction.
Absolutely.
That is so cool.
So yeah, I know we only have a little bit of time left. I do just want to kind of cut to the chase. But so what we're looking for with these very small telescopes, let me just show you these telescopes here. So we're looking for these objects, active galactic nuclei, sometimes called blazars or BL-LAC objects. They're highly polarized. Check. That means we can have another dimension or two dimensions over which we can look for violations. Or these ciphered galaxies, etc. I'm sure your listenership is astute and they will know about it. We built the small polarimeter, my colleague Gary Cole, class of 1969, I think he was, or 60, I forget what he was. Anyway, he's about 50, it was graduated 50 years ago, so we'll figure out how old he is. But anyway, he built this telescope. He's basically just a retired software engineer who moved from the Bay Area, from Silicon Valley to Western Reno, and lives up in the mountains at about 2,000 meters elevation, and takes these spectacular images with this robotic array of amateur telescopes.
This is not amateur. This guy's got game. I mean, this is like, I know what you mean. He's an unpaid professional. Let's put it that way.
he's not using the Keck telescope.
No,
these
but
are
he's
custom
building his own
celestron telescopes.
instruments, right?
Oh, he knows how to do it, yes.
Yeah.
And he knows how to analyze data. And he's not, he doesn't understand the theory as well as Andy did, or, I hope to, but he's incredibly astute as an observer. And he's taken part in observations of variable stars, of polarized stars, and so forth, that for campaigns that last 2 decades. In other words, he's looking at this particular star in polarized light over 20 years to see its full cycle of variability. He's just a phenomenal person. And so we made constraints and 2 papers. This one I'm incredibly proud of because this one I had to help get through after Andy's untimely passing this summer. And so again, we dedicated this in his memory. This is a tour de force. This paper, every day I get people asking me to can you also publish a version of your paper? And, I'm like, it's Andy's paper, in some book or some journal. And so we made a complete catalog in different colors, in different wavelength bands, and in different polarizations of what is known about these objects all over the sky. Because, as I said, you might want to look for a preferred direction, a reference frame that is universal, allegedly. In other words, that the vacuum of space-time singles out a particular direction would be a way to violate Lorentz invariance. We don't see that so far, but again, there are many, many different types of terms. There's many permutations of terms. In other words, you can look for polarized green light, or you can look for unpolarized violet light. So there's all these different permutations of polarization of frequency. Then you could take the frequency, which is proportional to energy, and you can ask if space-time has more than 3 dimensions of space and 1 of time, what would the effect be on the photon's energy? How would that change the photon's energy? So therefore, we look for energy or wavelength dependent effects. And there's an infinite number of them because you can just take the energy, raise it to whatever power you want, and you can set limits, as you say, on any of those. What's so spectacular about these searches that Andy pioneered is that with the simple instruments, not simple in the sense, but like inexpensive instruments that Gary put together called APOL, we are able to set limits on these terms that are competitive with a professional 3.6 meter diameter telescope that's bigger than the Hubble telescope by a meter. And we're doing this, literally with no money and just the love. And that's what amateur means, right, Chris? It means love.
For the love of. Yes, absolutely.
Exactly. And I know you have a lot of lovers out there. And so stay tuned for this. The next generation is really going deep and looking for what are called systematic effects. But I'm happy to take more questions.
Sure.
Your audience.
A couple of questions here. Okay. So, and I'm probably not going to Walla. Okay. Do any of these theories of everything, toes, trying to salvage 3 dimensions of space and 1 dimension of time, or they all operate as some assuming higher dimensions or hidden variables or something?
Yeah, very good question. So the answer is they do have other dimensions. In fact, some of the most promising, according to string theory, are so-called 10-dimensional models where you have 9 dimensions of space, 1 dimension of time, and even more so than that, what's called ADS CFT. There's a professor at the Institute for Advanced Study which is Einstein's, final resting place, so to speak, where he did his final work. That was essentially based on, whether or not you could make a theory of everything that would unify all the forces of nature in a gravitational fashion. In other words, in a purely geometric fashion, a gravitational, incorporating gravity and all the other laws, as we know in terms of the geometry of the theory of the strong force and the weak force and electromagnetism are all governed by what are called gauge groups. The thought was you could unify all of them together in a giant gauge group, and this still goes on. So my friend Eric Weinstein, who's been on my show many times, he has a theory that there are 14 dimensions of space-time. There is a theory by Garrett Lisi, who believes there's a fundamental theory that he calls E8, which is 8-dimensional exceptional Lie groups. And so Lisa Randall and her colleague Raman Sundram, who's not too far away from you, Christian, they believe that there's 5 dimensions, what's called Randall-Sundram gravity. So yes, the answer to the question is absolutely. There's more dimensions than meets the eye for many of these theories of everything, but we have no evidence that such a dimensionality is needed, and that's why things like loop quantum gravity are of interest to me, because it doesn't require more than 3 space plus 1 time.
Fantastic. Great answer. Thank you so much, Brian. And by the way, I forgot to acknowledge, I was scrolling back up while you were talking, Brian, just to look for other questions. I saw this really generous super chat from Pathmedic. Thank you so much. Before I get called out, thank you for. Oh, I'm sorry, I'm calling you out. I'm sorry, but I just want to thank you very much for the donation. It really does help. And yeah, super chats are gleefully accepted and appreciated, unless you're a student of mine, in which case you're poor and I don't want your money. But thank you so much, Pathmedic.
I'll take it.
That's okay.
I'll take it.
Let's get to another question here. And I know I saw it. If you'll put, and I did say if you can put a Q in front of your question. I realize I kind of got that in a little bit late, but I did see one other question from Dragarth1. Thoughts on Wolfram's hypergraph framework with continuous variable dimensionality, which unify GR with quantum through adding a space of. I can't say it all in one breath.
Okay, fine. I know about it because I had him on my show, and if you look behind me, I've had on everybody except Edward Witten. Ed, please hit me up. You got my number.
Come on, Ed.
So I had Stephen. I actually had Stephen and I had Eric separately and together, Eric Weinstein, and they battled it out in what I called a toe-to-toe battle. Get it? But the essence that we came to is that the unique thing about Stephen Wolfram's ideas in his physics project, which is over here behind me, is that the universe, yes, is described by this superspace of essentially what appear to be like a cellular automata that he calls bronchial space or branchial space, and that the branching of space-time occurs on an extremely radically fast pace, and that there are actually observable signatures that could arise from it. And those would be manifest in the properties of black hole coalescing to form gravitational waves. So the question is a good one in that we could possibly test at least the unification of gravity with the other forces in Wolfram's theory. The problem is that some of the timing and the techniques needed to do it are beyond what's currently capable of being done. So I would say for now, as much as I'm interested in that theory, we don't have yet a reason to believe that these rules that he proposes are really forming a basis not only for a theory of quantum gravity, but he claims for a theory of everything, which really means unifying all the forces and all physical phenomena into one.
And actually, Dragarth has a follow-up question, which I think you may have already addressed, Brian. But he also asked, "What about variable dimensions, where dimensionality is a free parameter able to change via phase transitions?" This is the part that gives me the heebie-jeebies because that's more parameter tweaking. But have you?
I don't have as much familiarity with that in the context certainly of Wolfram. But I will say that people like Hawking and James Hartle did claim that effectively time is sort of separated out from space. In other words, it once went from a state where what you call the future was actually a spatial dimension, and it's not so far-fetched because that's actually what happens inside of a black hole. All of your spatial directions are actually time-like towards the singularity. So they have in the no boundary proposal, Hawking and Hartle, essentially a changing of the nature of a dimension that we call time now, from having what they considered no boundary to eliminate the need for a singularity at the origin of our current observable epoch of our universe.
Okay, great. Thank you so much. And also, hey, shout out to the Exoplanets channel. There's also another great channel on YouTube. You got to check that out. Wow. It's called the Exoplanets channel. And great live. It's good to have you on here, man. Thank you so much. Let me just quickly double check a couple of things here. Okay. Oh, so yeah, here we go. Quick question. What is an answer to unlimited energy and world domination? Physicists should be able to answer that. Yeah, no problem.
Yeah, easy.
I've got it written down, but it's over there and I'm too lazy to go get mine.
I have it in the margin of my book on page 27.
Oh, so there you go. So check it's all in the footnotes, my friends. All in the footnotes. I think that's okay. So we are just a little bit past our time here. I do want to thank you again so much, Brian, for coming on the show again. You invited yourself. No, you didn't. Come on. I was looking forward to having you back, and we were just trying to figure out the time to get you on, and we got you on, and we made it work. And thank you so much for coming by. And I'd like to thank all of you so much for tuning in tonight and hanging out with us. And just as I close out here a little bit, I just want to say a very quick shout out and a gratitude to all of my Patreon supporters for helping to keep Launchpad Astronomy going, and especially to Anna and Travis Graham. They're over there. Travis Graham for their intergalactic level support, and Michael Dowling, Stephen J. Morgan, and Morrison Wild for their cosmological level support. Now, if you'd like to just help make Launchpad Astronomy work for the price of a cup of coffee every month, well, please head on over to my Patreon page. It's over there, and I'll figure this out one day. And all that. But anyway, feel free to check that out. Patreon.com/LaunchpadAstro. And as always, if you are interested in following along and enjoying this journey to this incredible universe of ours, well, please make sure you subscribe and ring that notification bell so that you don't miss out on any new videos. Until next time, I wish you all a very wonderful, at least for us here on the East Coast, a very snowy evening. And please stay home, stay healthy, and stay curious, my friends. Good night.